Hi students, I am Senthil Kumran from Department of Chemistry. Today we will going to discuss about the organic chemistry for chemical engineers. So in this subject we are going to discuss about the heterocyclic chemistry. In that heterocyclic chemistry, in that six-membered aromatic heterocyclic compounds. So how the structure involved in this pyridine and what are all the various resonating structure of the pyridine, then how to react with pyridine to other compounds, then reactions of pyridine, uses of pyridine. These are all the topics we are going to discuss about in this chapter. First, we are going to discuss about the structure and aromaticity of the pyridine. Pyridine is a six-membered heterocyclic compound with the molecular formula C6H5N and it is obtained from coal tar. So three types of electronegativity elements are available: oxygen, fluorine, nitrogen. So here nitrogen ringed with the benzene, that means C6H5N, we are called as the pyridine. So it may be formally derived from the structure of benzene through the exchange of one ring carbon for the sp2 hybridized nitrogen, another nitrogen compound. So sp2 means in the s orbital connected with two p orbitals to form the sp2 hybridization. sp2 hybridization means pi bond is involved. So totally three types of bond is there. That is the sigma bond, pi bond, then delta bond. So here pi bond is involved in the two atoms. Pyridine is an aromatic compound. However, the nitrogen's lone pair of electron in the sp2 orbital orthogonal to the p orbitals of the ring. Therefore, it is not involved in maintaining aromaticity, but it is available to react with the protons. Thus, pyridine is the basic compound. Why pyridine is the basic compound? Because here the electron is accepting the character. Acid means proton donor or electron acceptor. Base means proton acceptor or electron donor. Here the pyridine act as the electron donor, so it is called as the basic in nature. The next, so here given the skeletal structure of the pyridine. So in this molecule, the nitrogen containing the p orbital, the electrons are in the sp2 orbital perpendicular to the p orbitals. So here one more lone pair of electron here involved. Lone pair of electron means it is not involved in the bonding. So in that electrons act as the basic nature in the pyridine. So whenever the lone pair of electron containing in that molecule, that which will act as the easily in the basic in nature. So here nitrogen having one lone pair of electron, that is the non-bonding electron. Then resonating structure of the pyridine. So pyridine can be represented as the resonating hybrid of the following structure. So here 5 different resonating structure of the molecule here involved. What is the resonating structure? Resonating means stabilization or shifting of bond from one end to another end. So normally the benzene which act as the very good resonating structure. Why? Benzene having the alternating double bond and the single bonds are involved. So here in one carbon atom removed by the nitrogen. So in that nitrogen which is having the lone pair of electron, so in that no lone pair of electron involving in the ring structure, so the shifting of the electron from one carbon atom to another carbon atom here involved. So totally 5 types of resonating structure is involved. So in the ortho, para and meta position having the positive charges are involved. In the positive charge carbon atom which is easily accepting the electron, so that it acts as the very good basic in nature of the compound. Then another name of the pyridine is the azine. The introduction of the pyridine here. Pyridine has the very good aromatic nature. So here 3 positions are involved. One is the nearby the nitrogen atom act as the alpha position, followed by the beta position, then gamma position. So already I told the nitrogen compound, nitrogen element is the very good electronegativity in nature. So due to the greater electronegativity of the nitrogen relative to the carbon, so comparing to the carbon atoms, nitrogen having the higher aromaticity nature. So it tends to withdraw the electron density from carbon atoms at the position 2, 4, 6. Therefore, occur partial positive charge while the nitrogen atom occurs partial negative charge while the carbon atoms at the position of 3 and 5. Remainings are neutral. So this type of changes occur due to the resonating structure of the benzene. Then how to synthesis of pyridine? Commonly the pyridine structure having the 5 carbon atoms and 1 nitrogen atoms. So here ring breaking will occur at 1 and 5th position from 1,5 dicarbonyl compounds. So here we are taking as the 1,5 diketo alicyclic compound. It react with ammonia to removal of the 2 molecules of water to form the NH bond, So again it oxidized to remove the hydrogen molecule to form the pyridine. Another structure 1,5 diketo compound again react with ammonium acetate. So at a particular temperature to form the pyridine like structure. So these are all the 2 common preparations of the pyridine. Then another type of synthesis, Bonnemann cyclization reaction. So here we have taken as the 3 acetylene molecule. So here we have to take as the 3 acetylene molecule at the red hot tube at one particular time to form the pyridine structure. So it is the familiar method to form the pyridine molecules. Then Hensa's synthesis. Hensa's synthesis involved in the ethyl acetoacetate. The 2 moles of ethyl acetoacetate react with formaldehyde in presence of ammonia to form the dihydropyridine derivative molecules. Dihydropyridine derivative again react with the nitric acid with the oxidation to form the dihydropyridine derivative, another dihydropyridine derivative. Again it react with potassium hydroxide and calcium oxide in presence of heat to form the pyridine derivative molecules. Then from pyrrole. Pyrrole is the 5-membered ring nitrogen compound. It reacts with the chloroform. CHCl3 means chloroform. In presence of base, here I taken as the potassium hydroxide base to form the 2-chloropyridine derivative molecule. Again it react with the particular reagent to form the pyridine-like structure. Then by Diels-Alder reaction. Diels-Alder reaction which involves the 1,3-butadiene react with dicyanide molecule. Here we have taken as the 2CN connected molecule, dicyanide molecule in presence of 300 degrees Celsius to form the 2-cyanopyridine-like structure. Again it dehydration reaction to form the 2-cyanopyridine derivative. From this we have to prepare the pyridine molecule. Okay, now we are going to discuss about the basicity of pyridine. Pyridine is a weak base because it having the lone pair of electron. So it is an sp2 hybridized orbital. So it conjugated to acidic aromatic. So this pyridine molecule react with H+, that means proton acid, to form the NH bond, because this nitrogen donate the lone pair of electron to the hydrogen or proton to form the N+. The hydrogenated pyridine molecule is formed. In that molecule's pKa value is 5.2. That means pKa having the 5.2 in nature. So that it acts as the weak base. So it undergoes many reactions typical of amines, such as reaction with Bronsted acid, such as chromic acid and hydrobromic acid. So the pyridine molecule react with HBr, that means hydrogen bromide. So the hydrogen connected with the nitrogen, because the nitrogen having the lone pair of electron, that lone pair of electron donated to the proton hydrogen to form the NH bond. In that N nearby the N formed as the positive in nature. So in that positive terminal react with the bromine to form the CBr bond. So N having the positive in charge, Br having the negative in charge. Again it react with the Br2 for molecule to form the Br3 minus. So the compared to pyrrole, pyridine is much stronger base. Compared to the pyrrole, pyridine is much stronger base. This is due to the nitrogen lone pair is not involved in maintaining the aromaticity. Thus it free for protonation. However, in pyrrole, the lone pair on the nitrogen atom is already involved in the aromatic array of p electrons. Protonation of pyrrole on nitrogen atom results in loss of aromaticity and is therefore unfavorable. So here I given the example. in the pyrrole react with the proton to form the N bond H and H plus. Here the pKa value is the 3.8. So that pyrrole is the weak base, pyridine has the stronger in base, because pyridine has in the 6-membered ring compound comparing to the pyrrole. Pyrrole having the 5-membered ring compound, so that pyrrole having the less basic in nature compared to the pyridine. So then compared to the imidazole, pyridine is less basic. Compared to the imidazole, pyridine is the less basic. This is due to the protonation. The positive charge can be delocalized over 2 nitrogen atoms, while in case of pyridine it is delocalized over the ring which interpret aromaticity. That means compared to analogous aliphatic amines, pyridine is the less basic. Compared to analogous aliphatic amines, pyridine is less basic. This is due to the nitrogen atom in pyridine is sp2 hybridized molecules, more electronegative. Comparing to the other compound, here pyridine has the sp2 hybridized, so more electronegative, and the lone pair of electrons occupies an sp2 orbital. Thus it is held more tightly by the nucleus than the lone pair of electron in aliphatic amines. So with the sp3 hybridized nitrogen atom and the lone pair of electrons occupies in the sp3 orbital less electronegativity. So whenever in the molecule which having the sp2 hybridized orbital in that atom which easily donate the protons, that means accepting the protons, so that that having the higher in the basic in nature. Suppose in that molecule which having the sp3 hybridized orbital, so that there is no lone pair of electron in that position, so which will be the very less basic in nature. So here I given the decreasing order of basicity. So first one is the all the carbon atoms which are having the sp3 hybridized orbital, so that very low basic in nature. Then nitrogen 2 position, 2 5-membered ring, 2 terminal carbon atoms which act as the nitrogen. So it is the another type of the basic in nature. Then pyridine which is having the sp2 hybridized orbital in the nitrogen, so that it is the higher basic in nature comparing to the pyrrole which is having the NH orbital in the 5th membered ring, so it is the low basic in nature. Then chemical properties of the electrophilic substitution reaction. The negative pole in pyridine ring is at nitrogen, while the positive pole at carbon skeleton, which is opposite to what happens in pyrrole. So this is due to the greater electronegativity of nitrogen relative to carbon. It tends to withdraw the electron density from carbon atoms at the position 2, 4 and 6, which therefore acquire partial positive charge, while the nitrogen atom acquires partial negative charge at the carbons. At the position 3 and 5, which is the beta position, remaining neutral. So therefore these positions are the most preferred for electrophilic attack. So the electrophilic attack in the pyridine, which in the 3rd and 5th position, because in that 3rd and 5th position to forming the neutral in charge, so that which prefer to the electrophilic attack. So the inductive effect which involves in that pyridine molecules to form the resonating structure, the double bond character is shifting to the nitrogen atom. So in the form as the 2, 4, 6 positions are in the most positive in charge. So and in the accurate positive charges will be occur in that molecules in the 3rd and 5th position to form as the neutral in charge, so that here the electrophilic attack substitution will be occur in that positions. Then chemical properties of the pyridine. So first one is the electrophilic substitution reaction. So here three reactions are involved in the also as the consequences of the electron deficiency on the pyridine ring. Pyridine is less reactive towards electrophiles than ferrol and benzene. It resembles highly deactivated benzene derivatives where it does not undergo Friedel-Crafts alkylation or acylation or coupling with diazonium salts. Moreover, electrophilic substitution reaction of pyridine require very harsh conditions to take place and are low yielding. So in that pyridine first react with the bromine molecule in presence of 300 degrees Celsius to form the 3 bromopyridine molecule and 3,5 dibromopyridine molecule which is formed. So then the pyridine molecule react with the sodium nitrate in presence of acid H2SO4 300 degrees Celsius to form as the 3-nitropyridine molecule. Again this pyridine molecule react with H2SO4 in presence of mercurous sulfate at 230 degrees Celsius to form the 3-sulfonic pyridine molecules. So these are all the electrophilic substitution reaction occur in the third position and the fifth position because they are having in the more positive in charge due to the resonating in structure. Then reaction on nitrogen atom. 2-pyridine as a nucleophile. So as a tertiary amine pyridine has nucleophilic properties that it is react with the electrophiles. So pyridine N oxide is formed from the pyridine. So the pyridine react with the HCl to form the pyridinium chloride. So the nitrogen atom donate the lone pair of electron to the acid to form the pyridinium chloride. Again pyridine react with the methyl iodide to form the N-methyl pyridinium iodide. So here also nitrogen donate the lone pair of electron to the methyl iodide to form the N-methyl pyridinium iodide. Again pyridine react with the acetic acid at the room temperature to form the pyridine N oxide. So the nitrogen donate the one lone pair of electron to the acetate ion to form the pyridine N oxide. So here it is not acetic acid to form the pyridine react with the peroxoacetic acid to form the pyridine N oxide. Then 3 nucleophilic substitution on carbon atom. Pyridine is very reactive towards nucleophiles that benzene. It resembles benzene having strong electron withdrawing group due to the withdrawing effect of the electronegative nitrogen atom as appeared from the canonical structure of pyridine position 2, 4 and 6 carry partial positive charge. Thus nucleophilic substitution proceeds readily at the second position followed by the fourth position but not at a third position. This is due to the resonating form of the pyridine molecule. Additionally, attack of the position of 2, 4 or 6 results in resonance structure in while the negative charge is delocalized at nitrogen, thus it is more preferred while attack at position 3 or 5 results in resonance structure in which the negative charge is delocalized over carbon atoms only. So the resonating form of the localized structure here given. So the inductive effect, due to the inductive effect, inductive means electron withdrawing character from the nearby the atom. So this is due to the mainly occur in the electronegativity atom. The electronegativity atom which is having the lone pair of electron, which easily donate that electron lone pair of electron to form the resonating structure. So in the pyridine positions, which mainly from the 2, 4, 6 having the positive in charge because of the resonating structure. So in the 2, 4, 6 which easily attack to the nucleophilic substitution. So here given us the orientation of nucleophilic substitution in the pyridine molecule. So the pyridine molecule react with the nucleophile in the second position to form the nucleophilic attack. So again the nitrogen which is having the lone pair of electron to involve in that localized structure into the benzene ring to form the third and fifth position which forming as the negative in charge, and second, fourth, sixth position which easily attacked into the positive charge. In that positive charge, the nucleophile which is easily attacked to form as the new compound. So first one is the attack of the C2 more preferred, then attack of C4 also the more preferred. So the first structure we have the form as the negative charge in the nitrogen atom, and the first resonating structure. In the second reaction, the negative charge will be occur in the second resonating form. But in the third reaction, the nucleophilic attack at the C3 is very not preferred because the negative charge occur on the carbon only. So that first and the second is the more preferred. That means C2 attack and the C4 attack is the more preferred comparing to the C3 attack. So the C2 attack and the C4 attack is the mainly nucleophilic substitution reaction, the most preferable in the pyridine molecule. Three nucleophilic substitution reaction, that means C3 nucleophilic substitution reactions. So in the methylated pyridine molecule react with the sodamine, presence of ammonia at a particular temperature to form as the 2-amino 2-alkylated pyridine molecule, or 2,2- substituted pyridine molecule is formed. Then reaction with organometallic compound lithium reagents. So the pyridine molecule react with butyl lithium to form as the, so the butyl which is easily attacked into the C2 position to form as the 2-butyl pyridine molecule. Then three nucleophilic substitution reaction with the potassium hydroxide. So the pyridine react with the potassium hydroxide in presence of 320 degrees Celsius to form as the 2-hydroxypyridine. This is also the 2 attack. In the ketoenol tautomerism to form the 2-pyridone. Then reduction reactions of the pyridine. So the pyridine react with the H plus and LaH, that means lithium aluminum hydride. It is a very good reducing agent in presence of water to form as the 1,2 dihydropyridine. Again, Birch reduction. The pyridine react with the sodium and ammonia to form as the 1,4 dihydropyridine. Then pyridine react with the hydrogenation in presence of metal like nickel. So all the hydrogen atoms are removed to form the piperidine. So here all the carbon atoms which are having in the sp3 hybridized orbitals, sp3 hybridized orbital. Again the pyridine react with the Hi, hydrogen iodide, presence of 300 degrees Celsius, to form the ring opening reaction. That means pentylamine is formed. So these are all the various reduction reactions of the pyridine. Then derivative of pyridine, nitrogen N-oxide pyridine. The pyridine can be oxidized easily to N-oxide pyridine by peracids. So the pyridine react with the peracid at room temperature to form as the N-oxide pyridine. So on the basis of dipole moment studies, N-oxide pyridine is considered as a resonance hybrid of the following structures. So the positive charge appear at the position 2 and 4, thus active towards E+. E+ means electrophilic substitutions occur at the 2 and 4th position, second and 4th positions. So here given as the two different resonating form of the pyridine molecules. The positive charge appear at the position 2 and 4, thus active towards the nucleophilic attack. So second and fourth position is the more preferred to the electrophilic attack. Electrophilic attack at the third and fifth position, but the nucleophiles attack at the second and fourth position. So N-oxide pyridine as appears from the previous canonical forms. So these are the positive and negative charges at the position 2 and 4. N-oxide pyridine is more activated for the electrophilic and nucleophilic attack at the position than the pyridine itself. The N-oxide pyridines are very important intermediates for preparing pyridine derivatives that are difficult to prepare due to the essence of removal of oxygen atom by the reduction. For instance, nitrogen of pyridine is very difficult and low yielding reaction at the occur position 3. However, using nitrogen oxide, N-oxide pyridine will direct the nitrogenation to position 4, and then the oxygen can be easily removed by reduction as shown in the following scheme of the reaction. So here given as the different reactions of N-oxide pyridine. So the pyridine react with the nitric acid in the presence of sulfuric acid at 300 degrees Celsius to form as the 3-nitropyridine reaction. 3-nitropyridine, here it is formed as the 6% only. In that pyridine react with the peracid or hydrogen peroxide to form the N plus oxopyridine molecules. Again it react with the SOCl2. That means sulfonyl chloride to form as the 4-chloro-oxopyridine molecule and 2-chloro-oxopyridine molecule. So here fourth and the second positions which involves the chlorine attack. Again it react with the nitric acid to form as the 4-nitropyridine molecule. This 4-nitropyridine molecule again react with the reduction at in presence of palladium molecule and acid to form as the 4-nitropyridine molecule. Otherwise it will react with the PCl3, phosphorus trichloride, to form as the 4-nitropyridine like structure. So these are the various reactions of N-oxide pyridine. So today we have discussed different basic nature of the pyridine molecules and the resonating form of the pyridine molecule, then how it react with the ring and nitrogen in the position. So these are all the various types of the resonating structures of the pyridine molecules. Thank you.